Hi everyone. I want to talk to you about basics of probability and sample spaces. So when we talk about probability, we're always talking about a probability experiment. This is something that you carry out that has an unpredictable outcome. All right, so it could be throwing darts at a dartboard. It might be fishing, trying to catch that fish that you're looking for. It might be rolling a die or drawing a card. So all these things are different probability experiments. They all have an uncertain outcome. All right. Um, and what we want to talk about are the probabilities of different events occurring. Like, what's the probability that I hit the bullseye? What's the probability that I roll an odd number on the die? What's the probability that I draw a straight flush out of the deck of cards, right? So we want to compute the probabilities of these events. But to make all this concrete, we need to define what the sample space is, and we need to understand how to use it to get our answers. Okay? So let's go down to the paper here, and we'll take a look at this. So the sample space is the set of all possible outcomes. All right? So the set of all possible outcomes forms a set. All right? So we usually write this using these curly braces. All right, we list all the possible outcomes in this set. Sometimes the set has an infinite number of outcomes, and then this becomes a little bit more challenging. And there's other notation that you can use. All right, but in the examples I'm going to look at, we're going to use this notation where we can just list the possible outcomes, where we just have a finite number. Okay, and so let's look at an example where we roll a die. All right, so we roll a six-sided, and we always assume, unless said otherwise, that the die is fair, which means that every number has an equal chance of coming up. So we roll a six-sided die. All right. What would the sample space be? Well, the sample space would be the set of all possible outcomes. Right. So 1, 2, 3, 4, 5, or 6. These are the different numbers I can get. Okay. Well, what are the events that I might be looking for obtaining here? Well, I might be asking, what's the probability of rolling an odd number? Okay, so the events that I could come up with are descriptions of parts of this sample space. All right, so if I say odd, I can write that in terms of this sample space. Right? I can write that as 1, 3, and 5. Any of those outcomes constitute the odd event occurring. If I roll any one of those things, the roll is odd. So this is what it means to be odd. So the events are going to be subsets, smaller sets that are contained in the sample space, subsets of the sample space. So so to write down an event, you're always going to choose values from the sample space to write down your event. Okay? What if it was even? Well, that would be the numbers 2, 4, or 6. What if the event that I was looking for was rolling at least 5? Well, that means that I could roll a 5 or a 6, and that would count as at least 5. So there's my event. So you can see each event that I come up with has an associated set with it. Sometimes I might just be looking for the value of a particular roll. Maybe my event is just rolling a 1, right? Well, that's just the set containing that single element 1. But again, it is a subset of the sample space. So every event will be a subset of the sample space. Now, how do we compute probabilities of these events? How likely is it that these things are going to occur? Well, if we happen to know that every outcome in the sample space is equally likely, then we can do the following thing. Okay? So let's suppose all outcomes in the sample space are equally likely. Then we have this really handy rule, all right? If I want to compute the probability of an event, all I have to do is count the number of things in that event. So let me just denote that like this. And then divide by the number of things, outcomes, in the sample space. Sometimes people write it like this. Where these vertical bars, just like the absolute value symbol, they measure the magnitude of a number. Well, these measure the magnitude of a set. And if it's a finite set, the magnitude of the set, the size of the set, is just the number of outcomes in the set. So this is just the size of this set divided by the size of that set. The reason we use this notation is because sometimes we deal with sets that are infinite, right? And so it doesn't make sense to count the number of things in them, but you can still get a notion of how big the set is, even if it has an infinite number of things. Okay, so that's why this notation is used. But for the examples that we'll be looking at least for now, we'll be dealing with finite sets. So you can just think of it like this, just counting the number of things in there. Okay, so now that we've got that, let's see if we can compute the probabilities of these events. Now, the first thing we need to do is verify that all outcomes are equally likely. If that's not true, then you can't use this. All right? So let's verify that this is true. Are all these outcomes in the sample space equally likely? Well, the die is a fair die, right? That's what that means. A fair die means that every number is equally likely to occur, right? So because the die is fair, yes, this does satisfy that condition. All these outcomes are equally likely, and that's has to do with this. And like I said, if people talk about dice or drawing cards, you should assume that it's a fair die or it's a fair deck for the purposes of solving the problem. Now, in the real world, don't make that assumption. If somebody makes you a bet and has you draw a card, don't assume that's fair, all right? But when you see a math problem, they probably mean it's a fair die, all right? So that's a fair assumption to make, all right? So let's compute the probabilities, okay? The probability of getting an odd number. Well, it's the number of ways you can get an odd number divided by the number of things in the sample space. How many ways can I get an odd number? 1, 2, 3 ways. How many things are in the sample space? There's 6. So that's 1/2. The probability of rolling an odd number on a fair 6-sided die is 1/2. What about even? Well, it's the number of ways I can get an even divided by the number of things in the sample space. There's 3 ways to get an even number. There's 6 things in the sample space. So again, it's 1/2. What about the probability of at least 5? Well, how many ways can I get at least 5? Well, there's only 2 ways, right? So it's 2. And how many things are in the sample space? There's 6. That simplifies to 1/3. What's the probability of rolling a 1? Well, how many ways can I roll a 1? There's only one way it can happen, right? How many things are in the sample space? There's 6. Well, there's my answer, 1/6. So this is how we can compute probabilities. It's pretty straightforward, right? If we happen to know we have a sample space where every outcome is equally likely. Let me show you another example here. Let's roll 2 fair 6-sided dice. Okay? And what we're going to do is we're going to add their values. Sum their values. That's the experiment that we're running. Okay? So what's the sample space? Well, what's the smallest value I can attain, right? I happen to have a die here. The smallest number I can get on one die is a 1, and the other die could be a 1 too. That's as small as it could be, 2 1s. They add to 2. So the smallest number I can get here is 2. I could get a 3 by rolling a 1 and a 2, right? Or a 4 by rolling 2 2s, or a 5 by rolling a 3 and a 2. So I can get a lot of other numbers here. What's the largest number I can get? Well, I could roll 2 6s, right? If I roll 2 6s, I'll get a 12. I can't do any better than that. Okay, so my question here is, what's the probability of rolling a 7? Okay, well, you might say, well, hey, how many ways can I roll a 7? There's only one way to do it, right? It's only one, it only appears once here, right? And how many things are here? There's not 12, because I started at 2. There's 11. So it's 1 out of 11, right? It's 1. 7 is one of these things, and there's 11 of them, so 1 out of 11, right? No. What did we do wrong? We didn't verify that this set is equally likely, that every outcome is equally likely. And if you think about it, is it just as likely to roll 2 1s and get a 2 as it is to get a 7? Think about it. There's only one way to roll a 2. You roll a 1 and a 1. But how many ways can you roll a 7? You can roll a 1 and a 6, a 2 and a 5, 3 and a 4. There's many ways to roll a 7. There's only one way to roll a 2. So that right there, excuse me, that right there should be telling you that these outcomes are not equally likely. So we can't do that. Okay, so we have to be careful. There is a way to go about doing this, but I'm going to leave that for another exercise. Okay, there is a way you can represent the outcomes so that they are equally likely, but this is not it. Okay, so I wanted to present that for you just so you know to be careful. Okay, by the way, the probability of rolling a 7, if you just want to check it, ends up being 1/6. It's not 1/11. Okay. So anyway, I hope you found that helpful, and I'll see you in the next video.